Okay, so, all right, so question number 20. Which of the following methods is most appropriate to use to determine the number of different colored components in a sample of black ink? Okay, this one you just kind of have to know. Um, I think we tried to do one of these experiments in class and it worked with, varying degrees of success. But go ahead and just think about this, like read through the answer choices, then we'll talk. This. Okay. So does anybody remember what you would do in this situation?
Yeah.
Yeah,
See.
Column
I
chromatography
thought it was D.
I was thinking D as well.
and water is the mobile phase. Yeah, it's like that's interesting. Paper chromatography or column chromatography. Huh. One of the chromatographies would definitely work.
Because Dr. J, isn't that the remember the paper thing? Isn't that what we did?
We did paper chromatography, yeah. The range of, I mean, I kind of like the range of polarities here, so D makes a lot of sense, but I mean, determine the number of different colored components. No, probably D. Column chromatography would be better if you actually wanted to purify them. Yeah, D, correct, very good. Yeah, that was a tricky little question. Okay. All right, so 21. Okay, this is thin layer chromatography. Okay, so the diagram above shows thin layer chromatograms of the same mixture of two compounds. Based on the chromatograms, which solvent would be most effective at separating the two compounds if the same stationary phase is used for column chromatography?
All right. I'd say solvent C. That's the one where you see the most obvious split between the two.
Yeah, because the question's asking which solvent would be most effective at separating, right? Separating the two
Right.
compounds. And so you get your greatest separation here. Okay, that's pretty straightforward. That could be like an ACT question. Okay, does that make sense, everybody?
Yes.
Okay, let's move on. All right, methanol dissolves completely in water to form a solution that does not conduct electricity. Which of the following diagrams best shows the major type of attractive force that exists between the particles in solution? Okay, so this should be pretty quick. Go ahead and just kind of take a look at these and then let me know what you think the correct answer is. Okay, take 20 seconds or 30 seconds. Go ahead. All right, so what do you think, guys? What's the correct answer here?
I think it's going to be C.
Or D? Kaiten says C. What do you say, Ranisha?
I was gonna say A.
A. Okay, what do you think, Antonia?
C.
C. Okay. So, Antonia, why do you say C?
Well, I crossed out A and B, and I decided to go with C from C and D.
Okay, but there's a good reason to go with. So, why did you cross out A and B?
Because of the number of valence electrons or electrons.
Yeah, like this is all H3O plus, right? There's not much. Well, there's not much H3O plus in water. So the concentration in pure water of H3O plus is 10 to the negative seventh molar, right? So like there's just not much of this stuff. And then this CH3O, like it's just not going to be donating a proton here. Like this isn't a realistic interaction. And then there's no reason for this O minus here to be interacting with this O here. Like these are two electronegative things. They wouldn't be next to each other like this. And then you have to choose between C and D, right? And here we just really have to remember one of our two most important pictures in all of chemistry, right? And that's this picture of water, right? Where oxygen has a delta negative charge, okay, partial negative, and the hydrogens have partial positive, right? And so this oxygen over here is also going to have a partial negative charge, and this hydrogen is also going to have a partial positive charge. So this hydrogen bond here makes perfect sense, right? You've got partial positive and partial negative, and C is the correct answer. So then the question is, Rainisha, why is this incorrect? Why is D incorrect because of this interaction? What's happening there that should not be happening?
There's the bond between the two O's, and since they're both electronegative, or they both have a negative charge, they wouldn't.
Charge is good. They are both highly
wouldn't.
electronegative, so they're sucking electron density right away from their respective hydrogen atoms. Okay, So they've both got these partial negative charges. That's why this interaction can happen, but it's just not going to be an attractive interaction. It's going to be a repulsive interaction. So it's not going to be long-lived. Okay. Whereas this one over here on top in C, that is a long-lived attractive interaction. Okay, in a relative sense. All right. Okay, questions? All right, so we really need to have this kind of thing mastered because we could easily see this on the AP test. So we got to know this stuff. Okay, so let's take a look now at question 23. Okay, so a student adds a gram of an unknown brittle solid distilled water, stirs the mixture, and then measures its conductivity. Okay, the student repeats this procedure with more samples of the unknown solid and produces the graph above. Which of the following statements about the graph and the properties of the solid is correct? All right, so take 30 seconds or so to go through. Okay, so I want to hear from Rainisha. Rainisha, what do you think?
I was thinking that it may be between. I was thinking A and C.
Okay, so is it possible for something to be infinitely soluble? Look at that answer choice, right? Infinitely soluble. Is that something we've talked about?
No.
No, right? You can't just keep dissolving. Everything will saturate at some point. You can dissolve a lot of whatever you want, but you can't dissolve an infinite amount of anything in anything else. Okay.
Okay.
However, right? I mean, yeah, let's just leave that alone. So at least not some solid in water. That's not going to happen. Things can become miscible. So if you wanted to think of something as infinitely soluble in the sense of like two liquids mixing in terms of miscibility, but that'd be a terrible way to think of that. So this infinitely soluble thing, that's that's really strong language that the College Board is throwing at you. And whenever you see that kind of strong language, you should do a double take, like infinitely soluble. Wait a minute, we didn't talk about that term in class. I don't know what's going on there. But this one, right? Ionic solid that dissociates into ions. Okay, so we talked about this last time. So very good, Rainishi, because you weren't with us yesterday when we were talking about this. But or were you with us when we were talking about like molten sodium chloride? I don't think you were. So,
No, it wasn't.
yeah, so it dissociates into ions, right? And it's these mobile ions that allow for the electrical conductivity. So that makes a good answer. What do you think, Antonio? Is A correct, or did you get something else?
Yeah, I got it.
Okay, and Kaiten, you also?
Yeah, I got A as well.
Yeah, very good job, guys. Okay, A is the correct answer. Let's keep moving. So number 24. All right, which of the diagrams above best represents the interactions that are responsible for the relatively large solubility of potassium chloride crystals in water, and why? Okay, so which of these tells you why potassium chloride crystals dissolve in water and why? All right, go ahead and take, a minute or so to think through these diagrams. Again, this is the kind of question that I really do expect you to see, albeit in free response form on the AP test. Okay, they're just gonna have to ask these questions in which you have to explain diagrams or whatever and like talk your way through. So, because you can look up whatever you want, right? So you're gonna have a hard time looking up an answer to this question. So, okay, so go ahead and think through it and then we'll talk in a little bit. Okay. All right, guys, so what do we think here? We've got this situation. I want to hear from Kaiten. Kaiten, what do you think?
Oh, yeah, so I gotta take off here for just a second.
Go ahead.
But I got diagram A because what's gonna happen here is
Diagram 1, so answer A, okay?
diagram 1, right, answer A. Because like it says, there's that ion dipole interaction between the dipoles of the water molecule and the ions of the dissolved potassium chloride crystals, and that's what's going to pull them apart.
Okay, thank you, Kaiten.
Cool.
All right, so what did you get, Antonio?
I got A too.
Okay, and Rainisha?
I got A as well.
Okay, and so let's flesh that out a little more, right? Why are those water molecules oriented the way that they are? Why does that make sense? Who wants to take that on?
I can.
Okay.
So since potassium has like a slightly positive charge and
No, potassium
sodium.
has a positive charge. It's not slightly positive, it's positive. And chloride is
Oh, I
negative.
see it.
Yeah. Positive
So-
1 and negative 1.
With these charges and the way water is set up, with the O being slightly negative and the
Yes,
hydrogen
the O
being
is slightly negative and the H is
slightly positive.
Yes, partial
The way
negative.
they're oriented
partial positive. Very good.
makes sense.
Right, right. We got the partial negative here for the from the oxygen up against the positive K. And we've got the negative Cl up against the partial positive H, right? That's exactly what we should see. Okay. Is that what you were thinking too, Antonio?
Yeah.
Perfect. Okay. Number 25. All right. So which of the following best explains what happens as photons of visible light are absorbed by dye molecules? Okay. So this is a really interesting question. Think about what you know about electrons and so forth, and bonds, and then we'll talk in a little bit. Okay, so I'm gonna pause the recording. Whoa, okay. All right, so what do we think, guys? I want to hear from Kaiten. Kaiten, what'd you get for, oh, no, I already, we started with you last time. So Antonio, what'd you get for this one?
I was thinking between C and A, but I decided to go with A.
You decided to go with A, okay. And Ranisha, what about you?
I was thinking B.
B, okay. So then what about you, Kaiten?
Okay, I got A here.
Okay, let's take a look at all these, right? Let's start with, so nobody thought D, so certain covalent bonds begin to break and reform. That's not what happens when things absorb photons. At least not when a dye molecule absorbs photons. Interestingly enough, things like molecules can get photo bleached, so bonds can get broken over time. Like if you put if you expose some dyed fabric to light for an extended period of time, eventually that dye will degrade, and you won't see that color any longer. But just on a short-term basis, that's not what's going on. That's not the general effect. So see, the dye molecules begin to rotate faster in certain modes. No, that would happen if you were if they were absorbing. See, these are absorbing visible light. So interestingly, part C, that's what would happen if you were giving the dye molecules microwave radiation, not visible radiation. Okay, so your microwave works by making molecules rotate faster. So it actually causes the water molecules in solution to rotate faster, and that's what warms your food. So certain chemical bonds in the dye molecules begin to bend and stretch. Okay, that's infrared light absorption. Okay, so like this is stuff we could actually know. So this is like long term. Forget this. Then this is microwave absorption. Okay, this over here is infrared absorption. And then this guy right here, part A, that's exactly right. This is UV vis absorption. Okay, that's what happens just generally to molecules. So this is a really good problem whose explanations you can understand and memorize actually, because you could see this. Okay, you could very likely see these concepts. Like these are like units like 1, 2, and 3, right? Especially 2 and 3 are like, welcome Symphony, like these little hodgepodges of questions, and like you see all these different little questions here and there, and so you could end up seeing them any of this material later on. So okay, so I'm gonna go ahead and erase this bad boy, and then we'll move on to so A is correct. So then we'll move on to question number 26. And how are you today, Symphony?
I'm good. How are you?
Good, thank you. All right, so the IR spectrum above represents the absorption of certain wavelengths of radiation by molecules of carbon dioxide. Which of the following best explains what occurs at the molecular level? Okay, as the CO2 molecules absorb photons of infrared radiation. Okay, so we just talked about this. Go ahead and take just a minute or so to read through all the answer choices. So Ranisha, what did you get for this one?
I got A.
A, okay. And Kaiten?
Yeah, for this one, whoop. Oh, great, my thing tab back out. Yeah, here I got A as well, because the vibration you said is what happens when it absorbs infrared radiation.
Yeah. So Antonio, did you get A also?
Yeah.
Yeah, okay. So basically, increased vibration, okay, bond vibrations occurs when IR light gets absorbed. Increased rotational motion happens when microwave radiation is absorbed. And then electronic excitation, this is UV, ultraviolet, and visible light absorption, okay? And then this breaking reforming thing, no, I don't, no. That's not one of those three. Okay. So that's that. All right. So Symphony, does that all make sense? Those are just things we have to know. Okay. So alcohol versus carbonyl group. Nice. Okay. One type of organic molecule can be converted to another type through an oxidation reduction process, as represented by the diagram above. Which of the following best explains why infrared spectroscopy is an appropriate method to confirm that the product contains a carbonyl? Okay, let me go back to the previous problem really quickly and explain what's going on here. So these particular wavelengths, these energies here, okay, and the peak shapes correspond to particular bonds, okay? So in particular, like, or the whole darn thing can correspond to one bond. Like for instance, the carbon, like you've got basically one type of bond in this thing. So like the fact that you get this spectrum, this whole picture can correspond to just this molecule, okay? And in that molecule, there are two different types of bond vibration, okay? So there's the bond vibration that moves, it's easiest actually if you look at me. There's the bond vibration that moves the oxygens relative to the carbon, like, man, the only decent way to do this is, so I'm actually gonna stop the share for a second, is with my head. So there are two different kinds of bond vibration here, okay? There's this kind of bond vibration in which these two go in and out like this, okay? That kind of bond vibration, it's symmetrical. And there's this asymmetrical bond vibration in which relative to the central atom, they move side to side, so like this, right? Or from a different reference frame, you could look at it like this, okay?
Mm-hmm.
And that's the second type of bond vibration. All right, let me go. Where's my Chrome? There we go. Okay. So it makes perfect sense that we would see two peaks here. So that's what's going on, right? Like one of these peaks should correspond to one type of bond vibration and the other to another. Although I'm curious as to why they're so far apart. Like my explanation might be incomplete here. It's been a long time since I've thought about IR spectroscopy, and wouldn't you know it, my IR spectroscopy book is at school. So, but I think that general explanation will do for the purposes of this course. So, okay, let's take a look, and I'll Google a little bit just to make sure I'm on point sufficiently. So let's take a look here at this one. Okay, go ahead and read all the answer choices, and then we'll share out. Okay. All right, so here's a better classification scheme for bond vibrations. So you've got this twisting, right? Or symmetric stretching, it's called. So these guys are going in and out at the same time. Asymmetric stretching, one's going out while the other one's coming in. Wagging, which is like they're going back behind the board and then out toward you. Then you've got this like twisting here where one's going back behind and the other one's coming out toward. Then you got this dumbbell looking thing, and then you got this thing over here where they're kind of waving their arms. So I think so we talked about this symmetric stretching and asymmetric stretching, but you could also have scissoring and rocking within the context of, well, actually the rocking doesn't make sense. The rocking doesn't make sense in the context of CO2, but scissoring does. Scissoring absolutely makes sense. So I would go with those three as the primary stretching modes. Yeah, the rocking doesn't make any sense because your CO2 molecule would just be turning at that point. But this makes sense, and this makes sense. Yep. Does anything else make sense? Like, would you be twisting? Not really. You'd be turning your molecule. Would you be doing this? You'd just be doing this. It's just, these are equivalent. Okay, yeah. All right, so I would go with those three. Does that make sense, everybody?
Mm-hmm.
Yeah.
Okay. All right, we'll go back to the problem now. Sorry about the. Anyway, there we go. Okay, so then Rainisha, what'd you get for this one?
I got B for this one.
B for this one. Okay. Did anybody else get a different answer? Antonio, what'd you get?
No, I got B.
You got B, yeah. That's correct, right? So whenever you're talking about infrared absorption, you're talking about bond stretching, okay, or bond vibration. So,
Mhm.
because it could also be twisting or wagging or whatnot. So, B makes good sense, okay? B makes very good sense. Yep, that's what I would go with. Let's just double check. Yeah, no doubt. Okay. So, all right. Any questions about that? Okay.
No.
Number 28. All right. So, electromagnetic radiation with a maximum wavelength of 540 nanometers is needed for the study of the photoelectric effect in potassium atoms. Okay. What is the approximate frequency that corresponds to this wavelength? Okay. All right. So, this is our, oh, this stuff. Okay. So, we talked about this, but like, what is it like? C equals speed of light equals wavelength times frequency, right? Is that right? Yeah. So if this is the wavelength, then we need to find, this is the wavelength, then we need to find the frequency. Okay. So this is, I think the speed of light is 3 times 10 to the 8th meters per second. And then you're going to divide this by this lambda, okay, to find frequency. I'm just going to do a quick Google to make sure that like I've got that right. That's a physics formula. I didn't really anyway. So we do what we do think about this. We absolutely do think about this in chemistry. So it's just been a little while for me. So let me double check that that's correct. Does anybody else recall this formula? I think that's right. So C equals lambda F. Yeah, that's right. Yeah. So frequency. Yeah. That's totally right. Okay. So yeah. That's right. Okay. So that's correct. Okay. So equals lambda nu, where nu is the frequency. Okay. That's totally correct. So you can go ahead and do that, right? You can go ahead and do that with the information you've been given. Okay. So go ahead and give that a shot. And you're solving here, of course, for, yeah, frequency. Okay. Any questions before we get started?
Well, yeah, actually, this this is pretty simple here because the only one that would make sense, because okay, B, C, and D give you values that are massive, right? Hundreds of meters
So
per
let's all
second.
think through it, right? Let's all think through it. Let's take a minute and actually go through the calculation. Okay.
Okay.
All right. Very good. All right, so we're going to start with Symphony. Symphony, what did you get when you solved here for frequency?
I think it's C.
C, 1.9 times 10 to the 6th, okay. And then, Rainisha, what'd you get?
I got D.
D, okay. And Antonio?
I didn't finish my calculation.
Okay. And then, Kaiten, what about you?
Okay. I got A.
Okay, so let's look at this, right? So you've got 5.4 times 10 to the negative 7th as your wavelength, right? So let's just go ahead and redo all this. So C equals lambda times frequency, right? Which is going to be 3 times 10 to the 8th equals 5.4 times 10 to the negative 7th times what you're looking for, which is the frequency, right?
Mhm.
All right, and then drop there looking new. Okay, great. So we're trying to solve for this bad boy over here. Well, then we divide both sides by this number, right? And so when we do that, we get 3 times 10 to the 8th divided by 5.4 times 10 to the negative 7th. Okay, that's going to equal, right? Let's do 3 over 5.4. That's about 0.5. Let's call that 0.6. So let's go, so 0.6 times 10 to the 15th, which is like roughly 6 times 10 to the 14th. But that's your big indicator, right? Because you're dividing by a negative exponent, okay? So there we go, D.
Okay.
Okay, so that makes, that's the correct answer, sorry. So D is the correct answer, okay? So any questions about that?
No. Wait, so hold on. Actually, yes. So
And
this is a
seconds negative 1 is the unit, yeah, second, whatever. Go ahead, yes, Kaiten?
okay, so that's a massive number though. So
Yeah.
what is that so it's something per second. So how does that apply here?
That's the
So the
frequency.
wave.
So that's how many cycles per second
Oh.
that wave goes through.
Okay. Actually, yeah, that makes more sense now.
Yeah. hmm Yep. Yep. Okay. Anybody else have a question?
No.
Okay. All right. So let's go ahead and I'll clear the board. All right. And let's take a look at the next question. So this one, in an experiment on the photoelectric effect, a photon with a frequency of 7 times 10 to the 14th seconds was absorbed by a sample. What is the approximate energy of this photon? Okay. So different formula in this case. What is it? So photon energy, let me find it. So this one is E equals HF. Okay, so energy equals Planck's constant H times the frequency F. Okay, where Planck's constant is 6.6 times 10 to the negative. So Planck's constant is 6.6 times 10 to the negative 34th joule seconds. Joules times seconds. Okay, joule seconds. All right, so yeah, and we've got a frequency of 7 times 10 to the 14th. Okay, absorbed by some. So what's the energy? Okay, so this is pretty straightforward. Plug and chug. Go ahead and take 30 seconds and knock this out. So, all right. So what do we get for this one? So let's see. Rainisha, can you take us through?
Yeah, sure. So when you plug in the H constant and you plug in the frequency, it's 6.6 times 10 to the negative 34 times 7 times 10 to the 14th, which gets you 4.62 to the negative 19th. Round that up, you end up getting 5 times 10 to the negative 19th. So A.
Okay, that gives you A. Very good. Okay, and did everyone else get A?
Yeah, got Yes. A.
Okay, perfect. Any questions about this one?
No.
All right, very good. Let's move. Oh, one last thing though. It's worth talking about what the photoelectric effect is. So the photoelectric effect actually won Einstein his Nobel Prize. And it occurs when you've got a metal that's irradiated. So there's some light. And it's got to be at or above a certain frequency. That is an energy limit. So it has to have there's a minimal energy threshold for this. So light comes in, and what pops out is an electron, right? So photoelectric, photon, light comes in and pops out an electron, electric, photon, causes an electron to be emitted from the metal. Isn't that cool?
Yeah.
Yeah.
So
Mm-hmm.
I
Yeah.
feel like I've asked this before. Is that the foundation for how solar panels work?
No, it's not. The way that solar panels work is different. Solar panels have, golly, I learned about this when I was in college in inorganic chemistry. Solar panels, I'm going to try to give you a generic enough explanation that it explains it properly without introducing anything incorrect. Solar panels have their solid state they're solid materials, and they absorb photons, and that causes electrical current to start running. But it's an absorption excitation kind of thing, so it's an up and down sort of deal. It's not a photoelectric effect. You're not dealing with the metal like ejecting an electron.
Okay.
So you do have electrical current as the result of photon absorption, but it's not photoelectric effect. It's not like something like light coming in and popping out an electron, or yeah, or causing the emission of an electron. Okay.
Okay.
Yeah, it's a little different.
So Dr. J, where exactly would this photoelectric effect, like really, where would you really see that?
That's a good question. I don't know of any applications of it, but I'm sure there are some. I just don't know. Like that would be a good little project for you to kind of look into. Yeah,
Yeah.
I'm not sure. That's a great question. Okay, so And then Caton, for solar panels, the general term is photovoltaic. Okay, so you want to look up, like, if you're interested in this, you want to look up how photovoltaics work. And if you have any particular questions, you can ask me. I should be able to make sense of whatever materials you come across, because I remember it like pretty well actually, in terms of like the visual. Like there's this image I have in my head of like that represents excitation, but I don't remember many of the details from when I took inorganic chemistry in college. So you could totally look that up, and I'd be happy to chat with you about it. Okay,
Okay.
but
Yeah,
those are photovoltaic cells. Uh-huh. Go ahead.
oh, I just Googled photoelectric effect application. It's used in phototubes, which I guess are a thing. They detect light.
Cool. Okay. Nice. Anything else?
Uh, Application: solar cells, fiber optics, telecommunications.
I wonder how it's used in solar cells.
Yeah.
I wonder how maybe there is a stronger relation than I remember between photovoltaics and photoelectric. We should look into this. That's actually really interesting.
Okay.
Yep. Okay. Okay, so the frequency and energy ranges of photons in some parts of the electromagnetic spectrum are given in the table above. Which of the following could be the energy of a photon in the visible range? Okay, so so go ahead and take some time to think about this, and we'll resume in about a minute. Okay, so question 30. All right, so so what do we think here? I want to start with Antonio. Antonio, what do you think? What'd you get for your answer here?
I got C.
C. Okay. Did anyone else get C?
Yeah, I got C as well.
Okay.
I got C
Um,
too.
yeah, very good. Okay. Like that's the only number that's in between, right? You've got to go between 3 times 10 to the negative 19th and 5 times 10 to the negative 19th. And so it's right there. Okay. Very good. And that's the correct answer. Any questions about that? Okay.
No?
So we're going to move on. So yeah, I mean, the one takeaway from this, guys, is that the visible light range, the spectrum is really narrow, actually. So it's not a huge portion at all of the electromagnetic spectrum, which is interesting. Okay, so the absorption spectrum of a certain red dye is shown above. If a student analyzing the same concentration of this dye neglected to wipe fingerprints off the cuvette before placing it in the spectrophotometer, how would the absorption curve be affected? Oh, that's interesting. Okay, so fingerprints. Okay, so you're talking about absorption spectroscopy. Okay, so basically what you need to understand for this is that light has to get through this cuvette and be read. Okay, so it's the basically this thing is measuring the amount of light that's absorbed. Okay, so so go ahead and just think about that for a bit, and we'll talk through it in about a minute. All right, so let's go with Caton. Caton, what'd you get for your answer here?
Okay. Yeah, so I got B because so I don't think fingerprints would shift the curve to the right or the left, because that would mean it's absorbing a different wavelength, and
Okay.
it's not going to cause more light to be absorbed.
So this says less light will be absorbed.
Right.
Okay. All right. So okay, Rainisha, what'd you get?
I got B as well.
Okay, and then Antonio.
I got B.
Okay, and Symphony.
Between B and A.
Okay. See, I'm actually thinking it's A, so we'll double check since I've been known to miss these on occasion, but I think it's A because like the way that this kind of spectroscopy works is that the machine itself is actually measuring transmission. So it's actually measuring the amount of light transmitted. And so if it says to itself, okay, not very much is being transmitted at like such and such wavelength, then that means that we've got a high absorption, right?
Mhm.
So whether you've got a chemical in solution that's absorbing the light, or you've got a fingerprint blocking the light from coming through, you should see what would look like more absorption. So I would actually go with A on this one. So I think A is correct. Let's see what the actual answer is. I'll be floored if it's not A. Yeah, okay, very good. So yeah,
Okay.
that's what it is. I have to tell you though, this isn't a great question. There are a couple different reasons this isn't a great question, but I'm not a huge fan of this thing. Um
So yeah, in
yeah,
some of
let's just like I mean, your fingerprint could absorb the light. It could also scatter the light, but
okay.
and I don't like the fact that it says the peak of the curve would be higher. Like, yeah, sure it would, but like the whole curve itself could also be higher, right? You could see
Right.
like just a general because this fingerprint isn't necessarily like gonna absorb at these specific wavelengths, right? It's gonna
Mhm.
just block light all across the spectrum here. So you should actually just see a whole curve being raised up, is if anything, right?
Okay.
So that's what I would say. Okay. All right, let's go to question number 32. So a student measures the absorbance of a solution containing um, iron thiocyanide using a spectrophotometer. Okay, the cuvette used by the student has 2 frosted walls and 2 transparent walls. The student properly orients the cuvette so that the path of the light goes through the transparent sides when calibrating. How will the measured absorbance be affected if the student incorrectly orients the cuvette so that the path of light is through the frosted sides? Okay, so those frosted sides are going to block light. Okay, they're going to scatter it. All right, from being transmitted through. So very similar situation to the last one we talked about, and that is one thing I absolutely love about these questions. They give you a few of each type. Okay, to really go through. So, all right, take a minute or so to look at these.
Measured at the end, so it would think there'd be a higher absorbance.
Yeah, exactly. So B is what I got as well because the machine gets fooled, right? You
Mhm.
actually put the cuvette in wrong. So if it's in that incorrect orientation, the cuvette's just going to block a bunch of light, which would sort of make you think that there was more absorption, right? Then the solution would actually absorb on its own. So again, light blockage leads to what appears to be increased absorption. So B. Okay, guys, does that make sense? Like it's sort of like the machine measures transmitted light, right? So like you've got this light coming in, and then you've got your little cuvette, right? And if you accidentally orient it in the wrong way, and you have this frosted side, then most of this light's going to get scattered, who knows where, and it's not actually gonna reach the detector over here, right? So this is like your little detector. Okay, D for detector. So if you have the cuvette in the wrong way, the light doesn't get there. Okay, but if you put the cuvette in the right way, right, the light does get there. So in the instance in which it's oriented correctly, right, you've got your water, or not your water, your solution, and the light comes through, albeit maybe not quite as much light, right, but it still comes through, and so your detector can see that. So if it's oriented correctly, the light does get through, which means higher absorption, or sorry, which means higher transmission, lower absorption. Okay, so that's what's going on here. When you block the transmission of the light, the machine essentially thinks, or it gives you a reading that's consistent with higher absorption. Okay. Any questions?
No.
Good now.
We're good. Okay. Rainisha, Symphony, you guys good too?
Yeah.
Okay.
Yeah, I'm good.
Okay. So let's take a look at the last question here, number 33. A student uses a spectrophotometer to analyze a solution of blue food dye. The student first rinses a cuvette with distilled water. Then the student adds the blue dye solution to the cuvette, forgetting to rinse the cuvette with the blue dye solution first. The student places the cuvette in the spectrophotometer and measures the absorption of the solution. Assuming that some distilled water droplets were still in the cuvette when the blue dye solution was added, how would the measured absorbance be affected? Okay, so give us some thought. Okay, you could totally see something like this on your AP test, and we'll share out in a couple minutes. Okay, so I want to hear from Symphony. Symphony, what'd you get for this one?
I want to say D.
D, okay. And then what do you think, Antonio?
I think A.
And then Peyton
I got A as well.
and Rainisha?
I was thinking C.
Okay, so correct answer is A. It's clear to me that we just need to do some, like, this stuff is really pretty straightforward, but because we haven't actually done one of these experiments this year, which is my fault, right? We're not understanding this the way that we should. So we'll absolutely do these, but the correct answer is A, and I'll show you. So like, you just have to imagine, a colored dye, right? Like you've got some colored dye, and you're going to put it into your cuvette, and you expect it to look red, right? And then accidentally, you leave a few drops of water on the bottom of your cuvette, right? And it's got some little drops here, okay? And then you add your red dye, right? So after time, it's going to look a little less red, okay? And so if it's not as red, it's not absorbing as much light, okay? It's not absorbing as much light. So that's the deal, all right? So A is the correct answer. Does that explanation help?
Yeah, it does.
Yeah? Okay. So we just need to do more of these experiments. Like, it's clear to me that there's just enough spectroscopy here that we should just do some of them. We'll be able to do them virtually. So that's on my, I've made a mental note. We need to really go through like this hodgepodge of stuff and see it, because you could absolutely see it on your test. Like, this is the kind of material that the College Board could easily ask about on a conceptual basis. So we need to be ready for it. Okay. These make for great conceptual questions. Okay. So let's take a look now at the free response questions.
Dr. J, is there a way you can unlock the free response questions on our end?
No, I don't know why, but it's not allowing me to unlock them. So I don't know what the heck's going on there. Like, I've tried. I don't know what the issue is. Do you want me to like it just shows me a dead menu. I don't understand. So we're going to work on them together, okay?
Okay, that's fine.
They'll be on video, so you'll always be able to see them and go through them on your own that way. I'm sorry I can't unlock them. I don't know why it's not letting me do that. It doesn't make any sense to me. Okay, so answer the following questions related to xenon. So solid, oh, I see. Solid, liquid, and gas. Okay, oh, I see. So basically draw the particle diagram of the solid and then draw the particle diagram of the gas. Okay. So you could totally have to do this, right? So I want you to think about what these pictures would look like, and then we're going to describe them to each other, and then I'll do the drawing, or you could do the drawing if called. Okay, so go ahead and take like a minute to just sort of think about what they would look like and how they would differ from this, or even maybe more like 30 seconds. So so who wants to get us? So actually, because I think we should already know all of this, I'm just going to hustle through it. So the solid particles, right, are going to be stacked next to each other neatly and rigidly in place, right? So some neat arrangement of them rigidly in place. There's just not going to be as much space like you see all over here. There's all this space, right? And they're floating around, it looks like. Okay, so that's the difference. Does that make sense for the solid? Did we all get roughly that?
Yeah.
Yes.
And then the gas particles are going to be like flying all over the place. Who knows what they're doing? Just having a party, right? Okay, and space pretty far out from each other. And that works for you too?
Mm-hmm.
Okay. And then, of course, the solid particles are vibrating, whereas these liquid particles are sort of slipping, sliding, rotating, tumbling past each other, right? Okay. So in the box and diagram 2, gaseous, okay, great. Let P and V represent the pressure and volume of xenon in the container in diagram 3. If a piston is used to reduce the volume to V/2 at constant temperature, what is the new pressure in terms of the original pressure, okay? And then part C, describe what happens to the average speed of xenon atoms in the container in diagram 3 if the original volume is reduced to V/2 at constant temperature. Explain. Okay, so we're going to think about B and C, and we're going to think about them for, let's go like 2 minutes. Okay, so Caton, do you want to take us through part B?
Sure. Okay. So P1V1 equals P2V2. So if V2 is equal to V/2, then P2 has to be equal to 2P.
Okay, so let's go with that. So P1V1 equals P2 times, and again, this V2 is V/2, so this is V1
Right.
divided by 2, right? And so we can solve for P2 by multiplying both sides by 2 over V1. And when we do that, the V1s cancel out and we get 2p1 equals p2. Okay? Does that work for everyone, or do we have questions?
No, that works for me.
Antonio, all good on that one?
Yeah, I'm good.
Okay. You got the same thing, Ranisha?
Yes, I got the same thing.
Okay, and Symphony, all good?
Yeah.
Okay, that's out. Okay, then last one. Ranisha, can you describe to us what happens to the average speed of the xenon atoms in the container in diagram 3 as the original volume V is reduced to V over 2 at constant temperature?
So as the volume is or decreases, the speed would increase.
Okay, and is that what
there's-
you got, Symphony?
Yeah.
The speed increases because the volume decreases?
Yeah.
Okay, and then Antonio, what did you get?
I say that the speed decreases.
Decreases, okay, and Kate, what about you?
So I don't know that that volume has any bearing on speed, because speed is just a function of kinetic energy, right?
Yep, and this bad boy is at what temperature?
Constant.
Yeah, so that means that the velocity doesn't change. Okay,
Right.
so constant temperature means like no change in speed. Okay, the speed of the molecules, right? That they just are not changing. So that's the deal there. Okay, no change in speed. Let's see. So like the reason that like when V goes down, so like as volume decreases, pressure increases, right? Even at constant temperature, right? Why? Because even though the molecules or the gas particles, in this case atoms, aren't moving any faster, if you reduce the volume to a smaller volume, they're going to be just as many particles, right, in a smaller space. So they're going to be colliding more often with the walls of their container. And so because they're having more collisions with the walls of their container, right, we can say that their pressure has increased. Okay. So there is a distinction between pressure and speed of atoms, right? We can increase pressure just by decreasing volume without changing the temperature. Alternatively, if we heat, right, then we do make the atoms move faster. So we also, by heating, can increase their pressure. Okay.
Okay.
So any questions?
No?
All right, let's go through to the last problem here. So question 2. Let me just double check, make sure there wasn't anything else for question 3. No, it doesn't look like there is for question 1. What happens if you do this? Okay, good, it takes you to question 2, very good. Okay, so sodium chloride and calcium chloride. All right, so ions of a certain volume of sodium chloride, 0.2 molar, are represented in the box above on the left. The box on the right, draw a particulate diagram that represents the ions in the same volume of 0.1 molar calcium chloride 2, or sorry, calcium chloride. We don't pronounce the 2. Okay, so we have to kind of think about how this would work. So really think about the number of each type of atom that you have here versus the number of each type of ion you're going to need to have here. Okay, so go ahead and give yourself some time to think, and then we'll talk about it as a group in about a minute. What do you think is going to happen over here? When we go from 0.2 molar sodium chloride to 0.1 molar calcium chloride, what do you think is going to what's the first feature you would imagine seeing?
That there would be a lower concentration
Of what?
of the calcium chloride.
Okay, and so like over here on the left side, right, Caton's counted for us. We've got 4 here, and then we've got 3 plus 1, 4 there. So you've got 8 sodium pluses, right? So how many calcium 2 pluses would we expect to see on this side, on the right?
4.
Good. We would expect exactly 4, right? So 1, 2, 3, 4, because the concentration's been halved, okay? And so you go from 0.2 to 0.1, and there's a 1 to 1 stoichiometric ratio, okay, of sodium to calcium in this comparison. So we would expect 4 of the calciums. Okay, and so then, Antonio, see if you can knock this out, right? How many chlorides would we expect to see on the right side?
8.
8, very good, right? Because over here we have, good, we have 2 chlorides for every calcium. Exactly right. Okay, so that's exactly right. Does anybody have any questions about that?
Dr. J,
Yeah.
you know, I've seen before, like on diagrams, that there's the COs are connected together. Like, would you like that they're bonded together? Would they be bonded like that on this one?
Oh, in this one, no, because you're not, you don't have Cl2 as a molecule. You've got chloride ions that are going to dissociate as you drew. So your drawing was correct.
Oh, okay, makes sense.
Yep. Okay. So I'm going to go ahead and get rid of this. What like you're talking about like Cl that's molecular chlorine. That doesn't happen in this case. We're dealing with chloride, which is Cl minus. It's a mono ionic species. Okay.
All right.
Cool. Okay. Monoatomic ion. Okay. Presence of charged ions in ionic solids such as sodium chloride solid helps explain why it's soluble in water. Okay. And then what volume of 0.2 molar sodium chloride contains 10 grams of sodium chloride if sodium chloride has a molar mass of 58 grams per mole? Okay, so let's take like maybe 3 minutes to knock out these last two, and then we'll be all set for the week. Zoom. Okay, so we just discussed that for part B here, these ionic compounds dissolve because, as we've seen in other problems, right, the partially negatively charged oxygen atoms can orient toward the cations, in this case sodium cation, whereas the partially positively charged hydrogen atoms in water can orient toward the anions, in this case chloride anion. Okay, so any questions about that one? All right, so that's gone. Okay, and before I give Kaiten a crack at it, Rainisha or Symphony, would either of you like to take a crack at part C?
I was able to finish it, so
Okay, Symphony?
I'm kind of half-half on it, so
Okay.
pink.
All right, Kaiten, go for it, and then we'll talk about it, okay? We'll talk about a couple different ways to approach this one.
Okay.
So go ahead and, are you going to type your answer, or what do you want to talk us
Yeah,
through?
that's what oh, is it not showing as I'm typing?
Not showing. No, just talk us through it. Let me do the drawing.
Okay.
You talk.
So, oh, well, now it shows. Cool. Yeah, so basically what happens is we know we're given the molarity of the solution, 0.20 molar,
Mhm.
and we're given the molar mass of sodium chloride. So in 1 liter of 0.2 molar sodium chloride, there's going to be 0.2 times the molar mass grams sodium chloride, which comes out to be 11.6 grams. And then you need, so if it's 11.6 grams per 1 liter, how many liters for 10 grams? And so you do 10 over 11.6 gives you 0.86 liters to get 10 grams of sodium chloride.
Okay, and you could totally do it that way. I went with a slightly different approach, so I'll leave that up on the board, and you can take a quick screenshot if you'd like. But I'll show you a slightly different approach. So we always do C1V1 equals C2V2. So, okay, so it's like 0.2 mole per liter, right? C1 times V1, which we don't know, equals C2V2, right? And so like, in this case, what are we dealing with? So we've got, so this times how many liters, right, equals C2V2. Okay, so I was just like, so I was going to say to myself, like, we've got 10 grams of this thing, so how many moles of it do we have times some volume? Yeah, that's not exactly how I did this problem. So we've got 10 grams of this thing, so we've got, yeah. So that's what I did. Okay, got it. Okay, so it was actually simpler than that. So it's basically 10 grams of this. So if you got 10 grams of it, you've got 10 grams NaCl divided by 58 grams per mole will give you, it's about 0.16, but let me just get the correct answer here. So the more specific answer. So you've got 10 divided by 58 equals, oh no, 0.17. Look at that. Okay. So equals, yeah, that makes good sense. Okay. Equals 0.17 moles, right? So you got that many moles. Okay. So basically 0.717 mole per X liters equals 0.2 mole per 1 liter, right? And then you can just cross multiply and get your X. So X ends up being, just as Kaiten said, X equals 0.86 liters. Okay, so that's how I would have done that. I would just set up a simple proportion there. Does that work for everybody? Does that look pretty straightforward?
Yeah.
Yeah, that works.
Symphony, Rainisha, does that make sense?
Yes.
Okay. Symphony, you too?
Yeah.
Okay. All right. So that's how I would go about solving that one. Okay. Okay. So I'll stop the recording.